nice proposal. I guess my question is about the nature of the deformations. And I can think of two ways in which this geodesic model might be inadequate. One is, you may not be moving at constant speed along the geodesic, but as you say, as you grow from child to adulthood, your growth rate slows down as you near adulthood. And the other is that it may not be a one-dimensional path through your deformation space, but you may need a curved path through your deformation space. You might need at least two directions rather than one direction to summarize what's going on. Do you have any thoughts about this?
Well, you're absolutely right. The geodesic model is an approximative model, so it won't necessarily perfectly model all scenarios, particularly like you say, growth that starts off fast and then plateaus. But it is useful for statistical purposes. So as long as it can capture interesting trends in a compact way for statistical analysis, that's sort of our goal. Matching the data perfectly is sort of never going to happen with this kind of geodesic model. And we have other models actually that we've developed when we want to match the data closer. As for the second point about curves and the manifold, diffeomorphisms, so we do follow a curve.
So your question was about using polynomial regression,
for instance, but having two directions and moving at different speeds in each of the two directions.
Yes. That's an interesting point. I don't have an answer for that. Surely.
I think there is some work by one of your advisors, Stanley, which is dealing with this problem of time change also.
That's true.
So you can also embed some optimization of time change, which is really important.
Right. That has been explored. The idea of deformation of time as well.
Okay, another question? Yeah? Go ahead.
Hi, in compressed there are all these results about the number of measurements, the smallest possible number of measurements needed to reconstruct a signal given a sparsity level. Your experimental results on the number of control points needed, how they vary depending on the amount of sparsity in the momentum, seem to suggest that a completely analogous relationship might exist. I'm wondering if you've looked into how the standard compressive results could be extended in this particular case.
So I'm not terribly familiar with the literature from compressed sensing, and my experiments on the impact of the sparsity parameter is that what we saw, it usually has sort of a behavior that looks like this, where you have sort of an asymptotic behavior with respect to the number of parameters and sort of a linear increase in the matching error. So it's sort of an engineering problem, in my opinion, maybe because I am an engineer, tuning this parameter to your particular needs. What error are you willing to tolerate for a more compact statistical representation? And I don't know if there suggests that there's some optimal value. It's more or less for your application, how much error are you willing to have?
Yeah, there's a question. Yeah.
Partly a follow-up on René's question, because I believe that the results that we have on compressed sensing are based on the fact that the signal is really generated from the basis on which you're trying to make your compressed sensing. And here, in this case, we have one interesting question, which is that we don't know what's the right space of deformation. And in particular, when we look at the deformation which are here, all the deformation are generated from translation momentum, although we seem to see a global scaling. And if we have on Alzheimer, we see also local rotations, which are very hardly represented by the momenta, so the atoms of deformation that we have here. So one of the questions might be also what kind of results can we achieve if the model that we're using is false, which is most probably the case for any of the model that we're trying to set up, we are wrong anyway. So is sparsity still achievable when the model is false? That might be another question.
Okay, another question? I would like to answer this.
Small comment.
Yeah.
Because in this approach, as you mentioned, there are always errors. My suggestion is to try to use the probabilistic methods and sparsity enforcing priors, and this way not only you can probably show the deformation over the time, but at the same time have some measure of uncertainty for the results. That may be interesting.
That's a good point.
Thank you. Oh, great.
Thanks for that talk. So you do not have any control where the sparsity will spatially occur in the image. So I would like to know if it would be desirable that the sparsity would occur on the cortical structures or maybe on the contours of the structures.
That's a good point. Currently, there's no spatial preference for sparsity, but if you knew something about your domain, for example, if you know you're working with pediatric images, it would potentially be useful to incorporate that knowledge and adaptively sort of think about sparsity in different regions.
Okay, so I would just add just a few comments on that. Is that okay? In this, in fact, you have this about this control point. If you add as many control as you want, you're in a non-parametric setting. So more or less, you can deform in a full group of deformation. So here, in fact, reducing, we have built some sub-icing, some fine-dimensional approximation of something which is non-parametric. So in fact, we could, in terms of compressing, we could, in fact, inside the group, we could generate arbitrary deformation. So now we want to, I think the question would be to build a distance, maybe a distance between diffeomorphisms, and to look at the compromise between the number of parameters and the R2 elements. But I think this is very interesting. Okay, thank you very much.
Thank you.
Okay.